Okay, hi everyone. So now I'm going to solve three of the sample tutorial problems for lecture number 27. Specifically, for lecture tutorial 27, I'm going to solve number 1, number 4, and number 5. So first of all, question number 1, or problem number 1, is taking us back to the case of a spinning CD or DVD. These quantities are similar to what was in the previous lecture. And this is just trying to have you practice calculating a new quantity. So imagine that this CD or DVD has a moment of inertia, and you can suppose that maybe it's modeled as a perfect sort of cylinder, or maybe not. Maybe, it has a hole in the middle, etc. But maybe the manufacturer has measured its moment of inertia by trying to spin it up or spin it down. And we know that its moment of inertia is 6 times 10 to the negative 5. Okay, now what is the magnitude of its angular momentum when it's rotating at 200 RPM? And I've gone ahead and I've made the conversion for you from RPM, which is more of a frequency, to angular frequency, 21 radians per second, okay, to at least two sig figs. Okay, so angular momentum, the magnitude, is equal to moment of inertia times angular velocity. Looks like both of those quantities are given, so this is a pretty straightforward calculation here. So this turns out to be 1.26 times 10 to the negative 3, or we could have written that as a decimal. Okay. Now, looking at these quantities, I guess it's a two significant figure problem. So this will, I guess we would round this to 1.3 times 10 to the negative 3. Or if we wanted, we could maybe write it as 0.0013 instead of using power of 10 notation. Either way, this is that borderline case where maybe you might write it as a regular decimal, maybe use scientific notation. Looks like the answer is A. Now, if you were to double the angular velocity of this CD, and this is what happens in actual CD or DVD players, as the little laser and lens that's doing the reading moves from the inner radii to the outer radii of the disc, as you go from, let's say, the start of the movie to the end of the movie, or the start of the album to the end of the album. What will happen is the motor that spins that CD or DVD will need to change its angular speed, because they want the little read head to move along the surface of the CD or DVD at a constant linear speed. So that means changing omega. In order to keep V constant, you need to change omega to speed it up or slow it down as you move the read head inward or outward. So the question is, if the angular velocity here doubles, what would happen to the angular momentum? Okay, and then also what would happen to the kinetic energy? So first of all, just using proportional reasoning, without doubling the 21 to calculate what it is as at 42 and then calculate it all the way through, let's just use proportional reasoning. If the moment of inertia of the CD doesn't change, radius, mass, distribution of the mass, if all that's fixed, right, as it is for all CDs and DVDs, then doubling the angular speed, right, angular velocity, will do what to the angular momentum? Well, it looks like if we double the value of omega, then that means that we will double the value of the angular momentum L. How about rotational kinetic energy? The formula for that was 1/2 I omega squared. Notice here, kinetic energy depends on omega squared. So that means if we double the angular velocity, that means it will quadruple. the kinetic energy. Okay, because putting in twice as large of a value here for omega means that you will have to square that 2. So this becomes 4 times larger, right? The total kinetic energy becomes 4 times larger. So the kinetic energy quadruples. It looks like the one answer choice that has 2 correct statements in it is answer choice B. Now I'll leave it to you as an exercise, if you wish, to actually calculate all these things. There's enough information here to be able to calculate the angular momentum before it speeds up and after it speeds up, and the kinetic energy before it speeds up and after it speeds up. And you can prove it to yourself that this will actually work. However, I'm sorry, that this will be the case and this will be true. However, I really strongly recommend that you simply just exercise proportional reasoning by looking at the formula, and you don't have to actually perform the calculation to answer this question. Finally, let's use that right-hand rule that we just learned. If you see, if perhaps you could maybe look in a little window of the CD or DVD player, and you happen to see the disc rotating clockwise. So you see it rotating this way, okay? If we apply our right-hand rule to this, what direction does the angular momentum vector point? Now, first of all, let me remind you that the angular momentum vector has to point along the spin axis, the rotation axis. So the only 2 possible answers are going to be into the page or out of the page, because that's the direction that the spin axis lies in. So we just have to choose between into the page and out of the page, right? Or toward your eyes or away from your eyes. Well, now we use our right-hand rule. If our right-hand fingers curl clockwise, then our right-hand thumb will be into the page, right? So that will be away from your eyes, like this. I'm going to let my right-hand fingers curl naturally in the direction of the rotation, and then notice how my thumb points into the page, which is away from your eyes. So that means that's the direction of the vector. Great. Let's go ahead and move on to question number 4. So question number 4 is, it's basically an ice skater question. Let me show you what I mean. Suppose that we have a few children riding on a merry-go-round, and they all start near the center of the merry-go-round, so that the entire system has an initial moment of inertia of 750 kilogram meter squared. So our initial situation looks something like this. If we look down as a top view on top of this merry-go-round, I don't think it specifies whether the merry-go-round is going clockwise or counterclockwise. We'll just pick, it doesn't matter. Okay. So this is going to be some initial, I'm sorry, let me leave myself enough room to say this is the initial angular speed. And the initial arrangement has all of the kids clustered tightly near the center. Okay. So a lot of the mass of the merry-go-round is these children who are all pretty close to the spin axis. And then what they do is they all migrate out toward the edge. So that means that the final arrangement has all these same children close to the edge of the merry-go-round. Notice how the initial situation has some initial moment of inertia that is smaller, 750, because everything is close to the rotation axis. And then the final arrangement has a final moment of inertia that is much larger, 1,000 kilograms meter squared. And that's because all the mass is now far from the rotation axis. All right, what is the final angular speed of the merry-go-round after the children migrate outward, knowing that before they migrated, the angular speed was 1.5 radians per second. So we can use conservation of angular momentum And this is an ice skater, meaning we're treating, even though it may sound like there's 4 kids and the merry-go-round itself, let's pretend that we can treat it like a single object, and that the internal rearrangement of the mass is analogous to a spinning skater pushing their arms and legs from a, a tightly wrapped, a tightly packed configuration, spreading their arms and legs out into a more spread out arrangement. So that would end up increasing the moment of inertia. So let's write it that way. We'll just say, look, L initial for the entire system must be equal to L final for the entire system, assuming that things like friction or other outside torques are negligible during this brief time period. L is defined as I times omega. Now we can plug in all the values that we know. We're given these 3 values, and we can solve for our one unknown value at the end. And what we learn is that our final angular speed is going to be equal to 1.125 radians per second. Looks like it's about a 3 sig fig problem overall. So I guess we'll round this to 1.13 radians per second. So did the merry-go-round speed up or slow down? Well, the initial angular speed was 1.5. The final angular speed is 1.13. Is that what we would expect? So the initial angular speed was actually considerably faster, and the final angular speed is somewhat slower. Yeah, that's exactly what we would expect. That's what we expect when the ice skater rearranges their body from a more compact arrangement close to the axis to a more spread out arrangement where the mass is far from the axis. We see them slow down their spin rate. And that's exactly what will happen with the merry-go-round with the children. Part 2 of this problem is just asking, what's the change in kinetic energy of the entire system during this transformation? So this is just a pretty straightforward calculation. So let's just find out what it is. So change in kinetic energy. And by the way, another way to ask this question would be to say, what is the net work done on the system? In which case we would say, all right, work energy theorem says the net work done on the entire system by the children is equal to the change in kinetic energy of the system. So net work is just equal to delta K. So both of those would be equivalent questions. This would be K final minus K initial, where this is only a rotational kinetic energy. These are only rotational because remember the axis of rotation is fixed, right? This merry-go-round is on a fixed axle. So there's no translational motion of the system through space. Now, all of these quantities are all known. They were either given in the problem or we just calculated the last remaining one here up above. So now we can just plug in the values. Notice how I'm going to reclaim that extra sig fig that I dropped before, just to prevent round off errors. I ask my calculator what these quantities are, and I get 633 joules and 844 joules. And then I take the difference, and that's equal to negative about 211 joules. Okay. Now, looks like overall it's a 3 sig fig problem, so let's actually round that off to 3 sig figs now. Okay. All right. So what this means is the total kinetic energy of the system is decreased by the rearrangement of the kids, right? So the system lost kinetic energy. The kids overall did negative work on the system, right? And that, if we think about it, that makes a lot of sense. If we imagine the reverse, if the kids started out around the edge of the merry-go-round and they had to work really hard individually to pull their way to the center, fighting against that sort of apparent centrifugal effect, then what they would be doing is they would be exerting a force toward the center through a distance toward the center, and that would be positive work. And each of the children would be doing positive work on the merry-go-round system. And the merry-go-round would wind up with some net gain in energy by the time they were all done. However, this is the reverse of that. These children do have to hold on really tight, so they're exerting some force toward the center at all times, but their displacement is toward the outside edge. So in that case, what's happening is individually, their inward force and their outward displacement are in opposite directions. Cosine phi for the work done by the individual forces is negative, and therefore each of the children is doing negative work. And we take their network total and it's going to be negative. You could think of it in other ways too. You could think of it as, well, look, the entire arrangement decelerated. So there had to have been some sort of torque in the clockwise direction to decrease that counterclockwise velocity. So that means, okay, net torque clockwise, motion counterclockwise. That means that the net work done rotationally, torque times delta theta, would also have to be negative, and so on. So there's even other ways to think about it too. But overall, the kinetic energy of the system did decrease. Okay, the last thing I'm going to do is use question number 5 as one last example question. And I want to emphasize that this is optional. This is an example of using conservation of angular momentum for two interacting halves of a rotating system that have a common axis. Okay, so once again, you will not need to be able to solve these types of problems on any upcoming exams or problem sets or homework. But it's just in case you're interested. This shows you how to use law of conservation of angular momentum when there's more than one object. So suppose that we have a spacecraft that consists of two halves that can rotate relative to each other, but they're unequal halves. There's a smaller half and then there's a much larger half. So they have very different moments of inertia. So what we might sort of model this as, you might think of it as sort of having two halves like this, and they share a common axis. So this is their common axis of rotation. Okay. So how about I call the smaller half of the spacecraft here? Oh, it's already labeled number 1. Okay. So here, this is part 1, has moment of inertia I1, and the much larger half has moment of inertia I2. Okay, so much more mass, maybe much bigger radius as well. Okay, and they're connected here at this point right here, or at this sort of junction right here. Okay. All right. Now suppose that there's an internal motor here that starts to accelerate the smaller portion of the spacecraft counterclockwise. Okay, well, unfortunately, I've drawn a side view here. So to say that the smaller portion here is going to start accelerating counterclockwise, let's assume that we're looking from the right. So if we think of ourselves as being over here off the right side of the page, and we look from the right side, then we would see this direction here would be part 1 of the spacecraft rotating counterclockwise. Now let's make a prediction. What will the larger portion do? Will it rotate clockwise, or will it also rotate counterclockwise? All right, well, we know from the law of conservation of angular momentum that if everything started here at rest, then the net angular momentum of the whole system would need to be 0 at the start. Okay. And then, and that's true, everything did start at rest. If part 1 of the spacecraft starts to obtain a positive amount of angular momentum, which is our sign convention for counterclockwise, then part 2 of the spacecraft must start to attain at the same time some clockwise angular momentum. That would be negative. That way, when we add the positive to the negative angular momentum later, they will still add up to 0, just as they did at the start. So in other words, it's like a recoil. It's just like that helicopter. If the helicopter starts at rest and the blades start to turn counterclockwise, the body of the helicopter is going to try to start to turn clockwise at the same time as like a recoil. So we can make a prediction, but we'll see if it comes true when we actually apply conservation of angular momentum. Oh, one more prediction here, and that is whatever the angular speed of the smaller portion of the spacecraft turns out to be at any moment in time, what will be the angular speed of the larger portion of the spacecraft? Will it be faster or slower? Well, I think we can, again, thinking about the helicopter as an analogy, we know that angular momentum is equal to I times omega. So if the smaller portion of the spacecraft has a small I and a large omega, in order to be equal to that, we know the bigger portion has a much bigger I, so it must have a much smaller omega. So it's going to be a slower recoil angular speed. All right, so now let's actually test it out. Conservation of angular momentum. So let's add up the angular momentum of the two halves before they start to spin and the angular momentum of the two halves after they start to spin. So before they start to spin, we know everything starts out at rest. So all the angular momenta are going to just be 0 of any parts of the spaceship. So that left-hand side will be equal to 0. And then the right-hand side will be equal to the part 1 of the spacecraft. So that's moment of inertia times initial angular, or pardon me, final angular velocity, because the initial was 0, plus part 2 of the spacecraft. Now we're given many of these quantities. So for part 1 of the spacecraft, and then the final angular speed is going to wind up to be 1.2 radians per second counterclockwise. And then for the larger portion, $550,000. And then this is our unknown right here. So when we solve for our unknown quantity, we get that the final angular speed of the large portion is going to be about negative 0.0764. Okay. So rounding this off, it looks like it's sort of a 2 sig fig problem overall. So I'll round that off to 2 sig figs. And notice that that minus sign there implies that it will be clockwise, okay? As opposed to, so this one is clockwise and that one was counterclockwise. So it turns out both of the predictions are correct. Much slower than 1.2 radians per second, and the direction is opposite the direction of the other part of the spacecraft. Now, part C asks if this spin up, pardon me, up here spans a total of 120 seconds. So from rest up to, 1.2 radians per second for the smaller portion, or this negative 0.076 radians per second for the larger portion. What was the amount of torque needed in order to do that? Now, the question asks, what was the torque exerted on the smaller half of the spacecraft? So let's calculate it for the smaller portion of the spacecraft. So the net torque acting on the smaller portion of the spacecraft by the alternative version of Newton's second law is going to be equal to delta L over delta T. So if we just consider that smaller portion of the spacecraft, that's going to be equal to L1 final minus L, and that's just portion one. Portion one. This is omega 1 final. I got to keep all my subscripts correct. Great. Now we know everything started at rest at the beginning, so that would be 0. So that's going to be equal to this is the net torque on the smaller portion of the spacecraft on part 1. That's going to be equal to 350 Newton meters. And once again, this positive sign here means that it's counterclockwise, which is what we would expect because it started from rest and it attained a counterclockwise angular speed. So therefore, there must have been some net torque on it in the counterclockwise direction. Question D is going to ask, all right, during that same time period, what's the average torque exerted on the larger half of the spacecraft? Okay. And notice that no calculation is needed really to answer this question, although you could calculate it to find out. Okay. So at first, I think we should just think about it qualitatively. All right, we know from Newton's third law that if there is a torque being exerted on the small part of the spacecraft by a motor mounted in the large part, then that means at the same exact time, there needs to be a counter torque exerted on the large part of the spacecraft that is equal and opposite in direction by Newton's third law. So what that means is, without even doing any further calculation, we can use Newton's third law by extension and say, all right, it needs to, the torque exerted on the large part of the spacecraft needs to be opposite in direction, which we're just given as part of the question. And it needs to have the same magnitude, right? So it needs to be same magnitude and opposite direction. Another option would be to actually calculate it. So if we want to, we can say, all right, what's the net torque on part 2 of the spacecraft? And that's going to be equal to the change in angular momentum of part 2 of the spacecraft, the larger portion, over time. Now notice if the torque acts on the smaller half for 120 seconds, it must also act on the larger half for 120 seconds. Okay. There's no way that a force or torque can act exerted by one part of the spacecraft on the other can act in one direction for a different length of time than it also acts in the other direction at the same time, right? It's a simultaneous interaction. All right, well, then we can calculate this out. And this calculation is going to look very similar to the one that we just did here for part 1 of the spacecraft. Making sure I keep at least a little bit of extra significant figures to prevent round-off errors. Okay. And when I ask my calculator what this is, I get negative 350 Newton meters. So opposite direction, as this net torque here is in the clockwise direction, but same magnitude. The very last part of question 5 asks, okay, what's the change in kinetic energy of the whole system as a result of this whole interaction with of the motor spinning up the two halves? Okay. And does it increase or does it decrease? Well, we can already tell that it's going to increase because the whole system was at rest to start with. So all we need to do is just calculate what it is after the spin up is done. And we know it's going to gain a lot of kinetic energy. And where does that come from? Well, I don't know. It comes from whatever is powering that motor. So that's where the net energy gain of the two halves, this mechanical energy, kinetic energy gain comes from. So changing kinetic energy of the system is going to be the total rotational kinetic energy. Now this is, again, there's two parts of the spacecraft, two halves, at the later time minus k rotational total. Make it clear that these rotational and total at the earlier time. Now we can just go ahead and set this equal to 0 because everything started at rest. So we know it has no kinetic energy at the start. So the rotational, this is going to be the rotational kinetic energy of part 1 at the end, and the rotational kinetic energy of part 2 at the end. Okay, so all that goes into that term right there. So now it's just a matter of plugging in all of our MKS values. Make sure we square those angular velocities. And when I calculate this for my final answer, I get, well, here, let me show you the two halves. For my final answer now, I get 26,804 joules, or now this is roughly a 2 sig fig problem overall. So that would be 27 kilojoules. And of course, it's a gain, but that's for the reasons that we just discussed. That's what we would expect. All right, so that is that's the end of question number 5. Once again, question 5 with this sort of two-body interacting conservation of angular momentum type of problem is going to be optional this semester. But please do know how to use conservation of angular momentum to numerically solve problems that are more like the ice skater type of problem. And with that, please try and practice the remaining problems on the tutorial as much as you wish, or go directly to the Mastering Physics problems and try those.